So we've been through the transport layer probably more than any other layer. The thing that's the most difficult to try and grasp is exactly what's going on with TCP. And like with the rest of our chapters, our author has a little bit of a different take on things. And so I wanted to reinforce some fundamental concepts, primarily that the transport layer is concerned with processes talking to each other. And that usually excludes the routers, but we talk to the routers directly lots of times as well, like to configure them, for example. And when we do that, then the transport layer is running on that. I mean, of course they run all the way up to the application layer. They're Linux machines, and they have an Intel chipset. So they're just running a regular OS. And like all Linux, it has TCP/IP installed in it. So it's worth remembering that only the switch fabric down below is concerned only with up to IP, but the rest of the machine is just a regular computer. Okay, we don't need to spend much time on error correction, but I do want to go back and talk a little bit more about error correction number space, if we can kind of get to that a little bit. We talked about it in chapter 2 a little bit as well. Okay, so you guys remember that we're making ports talk to each other, processes talk to each other, and the network layer protocol and the transport layer protocol share that they're end-to-end. Not until you get down to layer 2 are you actually limited to what's going on a specific LAN. So these concepts, these ideas that I'm showing basically are simple. There is a lot of fun that comes from looking at pairs of packets and seeing whether the IPs and port numbers match or not and trying to discern what's going on. But that's usually something I torture the fundamentos de redes with, and we don't usually use that quite as much in here. There's been changes to the way port numbers have been used over the years. Where we're at right now is we have, and you'll see this in some other, I think I may have given one of the classes a homework on this as well. There are sort of official internet services up to about port number 1,000 or so. What this shows is that they're well known, but we've changed how we divide these up. What our author uses is the range that's published by the Internet Corporation for Assigned Names and Numbers, ICANN. And we can. So how do you, it's a good name, right? So I wanted to ask you guys, if I'm running NAT, and let's say I have a router, and it has a single IP address, and it's running NAT, so you have a table in here, and you can take one source IP and port number, and you have a destination IP and port number. I probably should have flipped those around because destination's over to the left. And here's your LAN, and you have addresses that you want to NAT. A few things to keep in mind. The addresses you're changing do not have to be private. You can run NAT anytime you want. You can run NAT to just change addresses. So if you're merging with another company, that's one reason why you might want to use NAT. You take their network and you NAT it into your own. And in 2 seconds, all of their systems can see yours, and you at least have a way back to them. Nobody has to change IP addresses, and you don't have to do anything to your routers to teach them about the other subnets. So that's a step in a direction for doing that. But how many different sessions can I have at a time with NAT? How many different people could be using this single IP address from inside this network? Anybody have a guess? Well, it's a huge number. It's 65,000 with just a single IP address, because that's the number you get when you take 2 to the power of the number of bits you have to keep track of port numbers. So it's 16-bit numbers. And you can give out 65,000 of these one at a time to a different pair of IP ports on the inside. This person gets this one, this person gets this one, and so forth. So it's highly scalable. and it's changed. But with software-defined networking, we think it's going to alter, because it'll just be a pattern matching rule that we push down. We won't have to have separate NAT servers anymore. So there's tons of those. They talk about socket addresses in here, and hopefully you guys still remember a little bit of that. Muxes and demuxes, queue this stuff up. I don't know if you guys have had computer architecture classes yet. You have? Okay, so how recently did you look at chipsets? Like, did you look at the Intel designs at all? All right, so I'm going to show you something that we've done to kind of make Intel's life more complicated. Salut. Okay, so we started off in the beginning with the CPU, and if you had something you needed to put on the hard drive or into memory, a program that was running, you handed the task to the CPU, and the CPU would go and do it. Sounds like an allergy. Well, I hope it's not a cold, if you're feeling okay. So the CPU would take the time to go do that. That rapidly became too slow because the drive and the RAM speed don't change. And so if your CPU needed 10 cycles to get something written to RAM, and you double the speed of your CPU, now it's going to take 20 cycles. And if you double it again, now you're going to waste 40 cycles. So pretty quickly, offloading this became a target of our architecture. So we came up with different schemes like PCI, where you could write in a language and hand it to the device, and it would go and accomplish the task and come back and tap you on the shoulder. Particularly when you're moving things to and from RAM or between RAM and disk, we had this concept called DMA. Did you guys study that at all? Direct memory access. So this is where you could write in a separate little language and give a task to the hard drive and tell it, go grab this program and put it in here in this location of memory and let me know when you're done. Or take what's in these locations of memory and write them out to the drive. I'm done with them. Can you please take them out of here? And so that saved those cycles to go and be able to do something else. So the implication that's important for networking is the ultimate resting place is on a drive, and then things need to get to RAM. And then you studied caches, I'm sure. So you had layer 1, layer 2, layer 3, or level 1, 2, and 3 caches before RAM, and things would gradually make their way up to the top, and then the CPU would be ready for them. And then any work that you produced, unless it was just going to be a temporary variable or something, it would make its way back down in the opposite direction, ultimately back to disk. So we built our whole industry around this kind of concept. Bring the tapes, load them into the mainframe, run the numbers, write it all back out, and then you're done for the month with the bookkeeping numbers, for example. So there's two things that are different about networking, about the internet, that has forced this model to explode, and it's caused Intel to massively redesign the way they handle I/O, particularly from the network inside their Xeon line of chips. And it's quite interesting. It's a very profound change. So it's, I guess you could have a little bit of pride in that you got Intel to kind of redesign itself around you, which is kind of what happened, I guess. And the differences are twofold. So I want to ask you guys some questions and see if you can come to the same conclusion, or if you can figure it out. Most of the time, when a piece of information comes into the computer, it has some value. You buy a CD, you buy a DVD, you download the file, you write a document, you write your homework, you update a spreadsheet. Those things you want to save until later. So you write them out to long-term storage. Maybe to Dropbox, but it's still long-term storage. Okay, with web pages, what do you do with them after you've looked at them in your browser? You throw them out. So it's a profound change in the way we've managed information. There's no reason to save a web page. So you've gone through all the trouble to pull information in, but this time the information's different because the model expects someone else to save the content. And it's not even, you're really just taking a glance at the content even. It's sort of put together in real time for you. So that's one change that puts a lot of stress on I/O, because You are constantly refreshing what you're looking at. You may take a look at a web page for a second or two after all that work and throw it out by just clicking on a link, and a whole new set of information comes in. So that moved the network card up to the position of being the device that now does most of the I/O on your system. It used to be the hard drive. It isn't anymore. It's dominantly the network card, and particularly in a data center or something like that. The second thing that changes is most of the time when you are pulling files in, downloading them, getting an email, pulling a file across from Dropbox, saving it out to your drive, there is not a program waiting, stalled on the next instruction that's waiting to read it at this very instant. You may download it like a Netflix movie and maybe watch it in 5 minutes or even in 5 seconds. That's not right now. But with a web page, usually the program is running and waiting for the data. You've put it in a queue for I/O wait, but there's no need to store the thing temporarily, and therefore for network traffic, what it looks like now, that's quite different, is network traffic comes in over the network and goes straight to cache. It bypasses the disk and it bypasses RAM. There's no reason for it to be there because you're just going to throw it away anyway. Right? So if you don't throw it away and you save it, that's like a whole special thing, dialog box, and you tell it what you want to name it and all this other stuff. So if you still use this old model, it's never going to work. And the problem with the cache is the cache sits on the chip. It sits on the surface of the chip. I'm looking for a really good red here, and here's one. So here's my modern Intel chip, and I have multiple cores. So I might have an 8-core system, and then I've got layer 1 cache that they each have, and then they all have layer 2 cache, which is a little bit bigger, and they share layer 3 cache. Well, it's not actually correct to draw it like that. It's more correct to draw it like this. You know, if I straighten up my tablet, I could draw rectangles where it wasn't tilted to the left so much. So this is the problem. You need I/O to be able to get directly into layer 3 cache. So what was designed specifically for our field, essentially, we're the ones that caused the problem, is they put an I/O bus right here and attach the network card directly to it. And the rest of your I/O is attached up here. So this is an area where what we're doing in networking and the advancements we made changed fundamentally the design of the processor that everything uses in data centers around the world. Right? So I don't think I'd ever seen that in my career before. These other changes where you offload work to subsystems and get them out of the CPU, those were things that were done because changes Intel was making. They were speeding up their CPU and they got tired of wasting cycles. And so they would make those changes to push it out. But this is one that we did to them. We pulled it in. It also caused network cards to get pretty super powered in their own right. Network cards are as fast as anything, as fast as the chips are now as well. So that's not covered in the book, and it's usually not talked very much about in network class. There's one author, William Stallings, nice guy. He covers it in detail. He makes the connection. Okay. So if you guys remember, you're basically trying to use flow control to kind of keep from overrunning the other end. What this basically shows is at the transport layer, you have your memory split up. There's the memory that's being produced, where things are being stored that need to go over the network, and then as it's pulled out, then it's being consumed. And it's very possible for this to fill or empty at any time. So the receive window message that we use in IP that is included in every packet to tell you how much space they've got is in part intended to do what this is doing, which is to keep from overrunning the person at the other end. Okay, so we send packets. Since you guys didn't have 2018 with me, I can't remember how much detail, because it's been too many weeks ago, I can't remember how much detail I went into explaining to you guys how we count bytes and not packets. Did I go into that in excruciating detail with you? I don't know that I did. Okay, so I like this diagram because this reminds me of a spiral staircase. And if you consider what's going on between the transport layer and IP, you basically have a train that shows up, it dumps all the passengers out at once, and they all have to kind of go down these stairs, more or less one at a time, to get on boats to take their little journey. And I'm sorry I'm using trains and boats, but this is the best example I've sort of been able to come up with. And every person gets a number as they go down the stairs. So what you do is you start filling these boats up with, and these people represent bytes. So you start filling the boats up, you put the number of the first person who got on the boat on the front of the boat. Boats can be different sizes, they can go different directions. Sometimes along the way, you have to get off of the big boat and get onto some smaller boats because the water is too shallow. So that analogy with sort of traveling around works pretty well with TCP and with IP. The problem is that most of the education that we get with the transport layer deals with packets. And you just have to remember TCP deals almost exclusively with bytes. It's counting bytes, it's figuring out how many bytes go in a packet. The number at the beginning of a packet is which byte number is there. Sequence numbers are byte numbers, for example. MSSs are byte numbers. When you have a congestion window of a certain size, it's sized in bytes, not in packets. And so some of the diagrams we use are a little bit confusing. This is a very traditional way of looking at a sliding window. And if you guys remember, based on your confidence, this window will change size. And I've never found a book that draws slow start and one of these windows at the same time. So you're going to see it here first. Maybe you've seen it before. So let's say this represents a very long stream of thousands of bytes that I have to send at a given time. What slow start will do, if you guys remember from TCP Reno, does anybody remember TCP Reno? You guys remember? This is, okay. So one of the things we have to do when we start using the network is we have no idea how much bandwidth there is. We don't even know who the routers are. How would we know what kind of connections they have? So you begin testing the network by sending one packet. And that packet contains a certain number of bytes that are specified by a variable called MSS, maximum segment size. It's how big your packet can be. The OS will give you a hint. It doesn't change as often as some of the other things do. So you start by sending one packet. If that goes well, you send two. If that goes well, please forgive my drawing, you send 4 and 8, and at some point you're going to get to a variable called a slow start threshold. Does this sound familiar at all yet? Once you get to the slow start threshold, then you're going to start growing by 1. So this is going to be 17, 18, 19, 20. See, they're getting, hopefully, they look like they're getting a little bigger until you have a loss. And once you have a loss, depending on the type of loss, you're going to drop back down to a small window size. So you're either going to drop back down to here, roughly, or you're going to drop back down to here. Okay, so the graph that you guys are usually seeing that represents this, that doesn't look like this, is a graph that instead seems to always be drawn like this. And what I show here, let me get some gray lines in here if I can to kind of help me a little bit. I'll make these, like each of these is worth like 5 or 4 or something like that. All right, and if you guys, I'm hoping some of this starts to come back to you as we look at this. This is your congestion window size, and this is transmission round. So these are rounds. This is round 1, 2, 3, 4, 5, 6, 7, 8, 9, round 10. This is your congestion window size in terms of MSSs. You have to multiply it by MSS to figure out how many bytes we're talking about. But here I send one segment, 2, 4, 8, 16, 17, 18, 19, 20, 21. And I'll continue on that way until I have a loss. The loss can occur at any point anywhere along here. So the way you usually see these diagrams drawn is in round 1, I send 1 packet. Round 2, I send 2. Round 3, I send 4. Round 4, I send 8. You can see it right up at the top. Round 5, I send 16. And then starting with round 6, I go 17, 18, whoops. Got to keep my scale right. 17, 18, 19, 20, 21. So do you remember this exponential growth until you reach the threshold? Whoops. Once you reach the threshold, then you start growing linearly. Why does it not change my color when I click on it? There we go. So does anybody remember any of this? Did you guys learn this in TC 2018? Nobody? Nobody remembers this? Oh, wow. Okay. Well, I just figured out what we're going to do for the rest of the lecture. You can't understand what's going on in a network without understanding, I think, in pretty good detail what's going on with TCP. So this is how traffic gets sent over the network. So I'm going to throw some acronyms at you. I'm going to take you to some websites. We're going to look at some stuff, but I need you guys to kind of do a quick study with me. For my fundamentals class, we spend weeks on this topic. It's that critical. It's that important. It's the hardest part of networking to learn unless you're doing routing, unless you're like a router jock. But it's also the most important to understand kind of what's going on, because this is where the magic is. What this implements is congestion control. This is what keeps the internet from collapsing. And before we got good at doing this, we would screw it up all the time and collapse it all the time. And there's very seldom one person that you can point to for an invention. Most things are debated forever. Like each country that cares to have a dog in this fight, there's a bunch of them. They believe they invented the airplane. And the United States absolutely believes it invented the airplane. And so does Germany, and so does Belgium, and so do a lot of others. So does Russia, or what was at the time. And they have evidence to prove it and all this, because these things usually happen in groups, and there's collaboration. They're not done in a vacuum. Orville and Wilbur Wright had gone many times to Europe and talked to people about their ideas. And so, there was this grouping of things. And this is true of the transistor and of the laser and even the telephone. People think Alexander Graham Bell invented it. Well, Elijah Gray would beg to differ. And Bell finally bought Gray's company to settle a bunch of patent disputes. It was just silly stuff like, did they pay off the guy at the patent office to put Bell's patent application in before Gray's because it showed up 5 minutes, 30 minutes later? They were that close, these two competing designs. And then Italy has its own history for this stuff. But when it comes to congestion management, although there were a lot of people who contributed, there is one person whose name stands out above all others, and it's a guy named Van Jacobson. And Van Jacobson, kind of like Moses, coming down from the mountaintop with the stone tablets on thou shalt not do this and that, he wrote a paper that turned out to be the seminal article, with the help of a grad student, on how congestion management ought to work in IP, in TCP IP. And so if you think about your computer is going to send data through who knows how many links, 20 routers from here to the other end of the network. What do you really know about those links? What do you know about the routers? What do you know about their buffers? What do you know about the transmission lines? What do you know? I mean, I'm sending packets right now over WebEx up to Richardson, Texas. Who can tell me how many routers it's going over? How big is the bandwidth from the back of that Wi-Fi router? Okay, what about the one that it leaves campus over a Lester's network? How big is that one? Do we know how big the one is to McAllen, Texas on level 3? We don't know any of that stuff. We know nothing about what's going on in the network. So how can a program that knows absolutely no details about the network's characteristics behave in such a way as not to overwhelm it? It gets worse. Not only do you not know anything about the network, but you don't even talk to anyone else to try to figure it out. You have no idea how many other people's packets are also being sent on any of these links. You don't know how many people are even on the local link getting to this first hop. So even if I told you the bandwidth, how would you figure out what your fair share of that bandwidth was? How would you know whether you could use all of it, or half of it, or a third, or a fourth? And so what ended up being developed, largely with Van Jacobson's name stamped on it, was this technique. And with this technique, you can figure all of that out without ever being told any of it. So it's as close to magic as you're ever going to see in networking. Right? And the way that it works is it makes assumptions about what probably is happening on the network based on the presence or absence of acknowledgments. And we've already talked about how we don't really have any idea when you write a protocol what's going on the other side, right? It's like an iron curtain that goes up. You really don't know why you didn't get an acknowledgement. Maybe your packet never made it. Maybe the system went down. Maybe you did get the acknowledgement, but it showed up corrupted, but the network did completely its part. You know, maybe you haven't waited long enough. It's coming. But in any case, you conclude that there's been a lost packet, because that's the only thing you can conclude. Because you can't know what happened, you can't change how you react. You always do the same thing. So let me give you an example. You're a general fighting a war, and you send a soldier out to check on the Germans, let's say. I'll make it a World War II kind of story. And you wait 30 minutes, and the soldier does not come back to tell you what he's seen. Do you know why? No. So what do? You send another soldier. And you're going to keep this up for a while before you finally conclude, we probably shouldn't be sending soldiers right now, right? Hey, it was your general that said soldiers are like chickens, okay? I mean, that was Santa Anna's most infamous quote of all. Oh, sorry. So, well, we're in Mexico, so I guess I made a bad assumption. I didn't know that. All right, so you will continue to send them, and you'll just send another one and another one until you decide it's not done. So that's what TCP will do. And the way you start off on a network is you try sending one packet. And if the packet makes its way back, you will take the acknowledgement and add whatever it was you sent to your total. So you'll go from 1 to 2. Now you can send 2 MSSs. You send 2 packets. For each one of the acknowledgements that comes back, you grow by another MSS. So packet 2 gets acknowledged. You now have a window size of 3 MSSs. Packet 3 gets acknowledged, which was the last one you sent as part of the 2. Now you can send 4 packets. So it's time for the next round. So what do I mean by round? You guys remember when we look at these simulators that we send packets in rounds. Here we go. So did you guys ever look at this when you were in 2018? Did you ever see this animation? Oh, wow. Okay. I don't know why. That makes me feel like I'm doing something wrong, though, I will tell you. But I couldn't imagine teaching a class without going over this. So this is a window size that doesn't change, which is not at all the way you would do it. But like I said, most of these diagrams, they never show you the window size changing at the same time they're showing you how the window works, which drives me crazy. So here I have a window size at the sender of size 5, and if I get packets, I can send them. And they get sent as a batch, and now I have nothing to do. I have to wait until the acknowledgments come back. Once the acknowledgments start coming back, my window will start sliding over to the right, and I can send another round. But you notice there's a great distance between when I can send packets. And when I do send packets, I send all that I can as fast as I can. So they're kind of all sent at once. You see that? So why is that? Why are they clustered like that? You're looking at it. I'm showing it to you visually, but can you convert it into a math observation? Why, even though I'm clicking send as fast as I can, things get sent in a batch, and then nothing happens for a long time, and then suddenly I can send another batch. So if you're the sender, what's going on? I'm always trying to send, but I can send a bunch of stuff, and then I have to wait a long time, and then I can send a bunch of stuff, and I have to wait a long time, and I can send a bunch of stuff, and it takes, that's the way my whole day goes. So why is that? What is it about the network that forces us into this type of behavior? Why isn't it evenly spaced packets all day long? One, and then another, and then another, and then another. Why would you have a network where you dump everything you can as fast as you can, and then you wait a long time, and then you send more? You do it to avoid congestion, right? And you send enough stuff, you'll also get collisions. But we can recover okay from some collisions. If something collides, your layer 2 is responsible for resending it. It'll keep a copy. Layer 4 will usually never know about it. Like Ethernet, Ethernet keeps a copy of every frame it sends, and it'll recover itself from collisions. You do not have to go and ask the application again for help. And it's a good thing because what the application gave you may bear no resemblance at all to what you're trying to send in Ethernet, because it may have been broken up into 10 different frames, and he's like, how would I know what you're trying to send? I don't recognize this at all anymore. So Ethernet keeps a copy of the frame and will resend. Like Wi-Fi, it will hold on to one, just one. So it's like windowing a little bit, but it does one at a time. So collisions play a role in this, but that's not the dominant reason why we send stuff like this. So tell me about, make a guess. I want you guys to make a guess on the bandwidth of the network that leaves the campus at Monterey and goes to our campus in Guadalajara. How many megabits per second or gigabits per second would you guess it is? Just based on networks that you've seen and what you would hope it is, maybe. What do you think? How big would a network be? 500, so half a gigabit per second. All right, so 500 megabits per second. There's no wrong answer to this. Okay, so if I have a window size of 5 packets, and each one of them has 1,500 bytes, I'm going to do a little math here. And each one has 8 bits. That's 60,000 bits I'm going to send in a window. And he says I'm going to send it over a network that sends 500 million bits per second, right? That's how long it's going to take to transmit all of those bits onto my wire. 0.00012 seconds. So if I multiply it by 1,000, it's 0.12 milliseconds. It's 120 nanoseconds. Right? So 0.12 milliseconds. That's what I want you to remember. 0.12. So less than about 1/10 of a millisecond. All right. So if I come up here and I open up a system here, and what I'm going to do is try looking around for just a second for something I can find at Campus Guadalajara. I don't know if I have any luck doing this at all, but usually I can. Okay. Okay. This, maybe we'll find something. here's something in Guadalajara. It's something from the government of Jalisco. So what I'm going to do is stop this, and I'm going to grab this URL, and I'm going to come over to my window. Can anybody guess what I'm going to do? I'm going to ping. That's not going to work, so I got to get rid of this. Oh, how rude. All right. There. All right. Now it's starting to make me mad. Does anybody know a big company that's based in Guadalajara? There's a big Intel plant. There's a huge Oracle office. They hired tons of tech people. It's the best paying jobs in Mexico for engineers, supposedly. There's a $4 billion Cisco plant, but all of those companies are headquartered other places. What I want to find is something that I can ping that's based there. But let's just try pinging something maybe that's just about as far away, like something in Houston. That's similar distance. All right, how long does it take me to get a packet there and back? 37 milliseconds. So the distance to get there is half of that, but which is bigger, the transmission time or the propagation delay? How long did it take us to transmit that whole window on his network? 0.12 milliseconds, and now it's going to go for 37 milliseconds. Thousands of times more sometimes, hundreds at least. So you can dump your entire buffer, your entire window onto the network quickly, and then you have to wait to get acknowledgments back. If your window was bigger, you could continue sending for longer, but you're not willing to do that forever because at some point you are going to find that your network is congested. It's reached its capacity. You don't know where, you don't know at which link along the way, you don't know why, you don't know if you filled it up personally or if a bunch of other users happen to just log on right now and it had nothing to do with you at all, or if you're the only one that's noticing this, but it doesn't matter. You can't know. All you can do is resend. But because congesting the network can cause it to collapse more or less instantly, what TCP was designed to do was have a huge reaction. When TCP believes that there's been congestion, if it thinks it's lost a packet, it will cut its window size in half, if not all the way down to 1. It's a very dramatic reaction. So it increases linearly and decreases exponentially. So if you've ever heard of TCP being referred to as a sawtooth protocol, this is what they're talking about. This is what this looks like up here. Okay, so what you need to take away from this is the dominant amount of time that you wait in networking is for propagation delay, the time and the delay inside the routers. The time it takes you to transmit is nothing compared to those. We're really good at transmitting. So I send a bunch of stuff. This is why it's not spaced out, because your transmission time is super fast. So you'll start by trying to send 1 and seeing if the network can handle it. Then you'll go to 2, then you'll go to 4. Your operating system is going to give you a suggestion by giving you a variable called slow start threshold. So this mode, when you grow exponentially, is called slow start, or SS people will call it. So that is in this mode here, slow start threshold. Once you reach this variable where the OS has basically said, I think you should probably stop around here, and it'll get changed. It's just an initial suggestion. Then you enter what's called congestion avoidance, or just CA. And you will go like this forever and ever and ever until you believe you've experienced a loss. But you'll grow 1 by 1 by 1. So the idea is generally that the OS believes that somewhere between here and where you would have grown next, which is from 16 to 32 in our particular case, because we were at 16 when we hit the threshold, we think, for who knows why, that you're going to congest the network, you're going to lose a packet somewhere between here and here. So inch your way forward. Just go very slowly from this point. And you may have a loss here, you may have one at 40, who knows where. Once you have a loss, and let's say this continues on up to 24, and then one more up here to 28. When your window size is 28 packets, you are sending 28 times MSS bytes, so it's a lot of bytes. You have a loss. And what the loss is going to cause you to do is first set your new threshold to 1/2 of what your window size was. So here's your window size. You're going to set your new threshold to be 1/2 of that, which is 14. If you think that your loss is just kind of a momentary blip, then you will also set your window size to 14. But this is for sure going to be the new SS threshold, the new one. If you think the network just stopped working, you're not getting any acknowledgments back at all, and you're like, oh no, I've like collapsed the network, then you will drop your window size all the way back down to 1 again. And you will grow exponentially up to the threshold and then linearly, and you'll repeat this over and over and over all day long. All right, so let me show you a couple of websites that make this a little more clear. I don't know if it's this one or not. I'm trying to get my head wrapped around this that you guys didn't look. So here's a simulator that came from that textbook, Rose's book, the one you guys used in 2018. And what this shows, it's random. Every time I hit reload, it's going to draw a new graph. And the idea is for you to try to figure out how to label what's going on here. So what I'm going to do is take a picture of it, come over, and give us a chance to kind of play around with this. So one of the things that's kind of hard to see on here is they also give us kind of a random SS threshold, but it's very light colored or it's very small. It's this red dot that you can kind of see at 8. Okay, so that's my first SS threshold. So what my rule says is with slow start, I start with 1 and I double every round. And what I'm doubling is the number of packets I'm willing to send at a time, the number of soldiers I'm willing to send out of camp and at a time without getting nervous about whether they're going to come back. So if I send 1 out and he comes back okay, great. Maybe I can send 2 out. They won't get discovered. That worked out great. I send 4 out. At some point, one of the captains is going to come up and go, hey, General, I think you should like knock it off. They're going to discover you for sure. You're sending too many people. Okay, let's stop doubling it every time. Let's just add 1 soldier at a time and see how many people we can get over there, and they can tell us whether they made it or not. So that's kind of what's going on. So I never got that far with this example, because what happened in this example is I went 1, 2, 4, and I had a loss. And I know that the loss was one where I think the packet is actually gone. The network stopped working because I changed my window size back down to 1. If it hadn't, then I'd change it to something else. So say, what's my rule? I have a loss. So you set the new threshold equal to the old one divided by 2. So that means my new threshold is, because my window size was 4, that's actually, I didn't quite write that right. That's not exactly correct. Your new threshold was your last window size divided by 2. I don't know why, I'm losing my mind. So my window size was 4. Therefore, my new threshold is going to be 2, and I can draw that as a line. So my new line is down here. The second thing I have to do, now that I know my threshold, how much do I want to start sending? Do I want to start sending at the threshold? Do I want to start sending less? And that's going to depend on the version of TCP you're running, but most of us use TCP Reno. That's the version name that we use, and it's also the one that's taught most of the time. And so you have two choices. Choice A is if you think there was a total loss, the network stopped working. And in this case, you're going to set your new collision window equal to 1. Your second option is you think the network's still working, sort of, and you have evidence of that by what's called a triple duplicate ACK. It's like a backward somersault. It's got a heck of a dismount. It's really kind of cool. We won it in the Olympics last year. I don't know if you guys saw any of that or not. If it's a triple duplicate ACK, it means the network is still working. Just one packet in your window was lost, but the other ones look like they made it. Then there's no reason to overreact and go down to 1. So in that case, your new congestion window will be equal to the new threshold that you just set. So in this case, I know that they felt like they had a loss because I can see they went all the way back down to 1. All right, then they grow exponentially to 2, and they've already reached the threshold. Now they have to grow linearly. 3, 4, 5, 10, 15, 20, 25. They get to 27 packets in their window, a window size of 27 MSSs, and they have another loss. One of the packets doesn't make it. But this time I didn't go down to 1, did I? This time I went down to a different number. What number did I go down to? Well, we can calculate it. So this is 27. Half of 27 is, if you round down, 13 to be conservative. So the first thing I'm going to do is set my new threshold to 1/2 of my window size. So it's now going to be set to 13. And I'm going to set my window size to that value. So why isn't my line on that, why is my blue line above it? Because with triple duplicate ACK, I get credit for the 3 ACKs that got sent, so I add 3 to this. It's complicated, but that gets me up to 16. And I'm stayed above the threshold, so I'm automatically in linear growth mode. I only grow exponentially when I'm in slow start. Once you pass the threshold, you're in congestion avoidance. So if I draw these areas out, I'm in CA here. I'm still in CA here. This loss here was a triple duplicate ACK loss. This loss here was a timeout loss. My timer went off, so it was a total loss. I'm in slow start here, and I'm in slow start right here. Everywhere else in the diagram, I'm in congestion avoidance. Let's look at another one. It'll help to go through several of these. This one's more interesting. Okay, let's do another one. All right, I start off in slow start mode. I'm beginning to get a suspicion that the threshold always starts at 8. But at any rate, here it is. And it's going to stay there until I have a loss. So I'm going to draw the line over further this time. Because you can see where the loss is, the window size goes down. So it's just where you head downhill. So here's my threshold. It's set to 8. So I'm going to grow 1, 2, 4, 8, right? Grow exponentially. Once I get to 8, I'm no longer in slow start mode. Let me pick a different color here if I can find one. I'm now in congestion avoidance. And my window keeps growing 1 by 1 by 1. So that means every transmission round, I add 1 more MSS's worth of bytes to my window and dump all of it as fast as I can onto my network. It has to be broken up into packets, but that's why people say your window size is how many packets you can send. It's never how many packets you can send. It's how many bytes you can send. You divide it up into MSS's and you get the number of packets. But TCP is not counting packets. It's counting bytes only. The sequence number is the byte number, not the packet number. All right, so I have congestion avoidance. I got to 15, 16, 17, I got to 18 here. And I know I had a timeout loss because it went all the way down to, no, I had 2 losses in a row. The first loss I had was a triple duplicate ACK because my next window size was 1/2 of 18. My threshold is now going to be set to 9, and it's going to last for about 1/10 of a second. And I didn't set it to 9 because I add 3, 10, 11, 12. So then my window size was at 12 for the next communication round. And I had another loss. This time the timer went off. That's what I get for trying to send too much. So this one went all the way down to 1. So this is a modest loss. I didn't drop all the way down to 1. This one is a hard loss, and I dropped all the way down. You will hardly ever see 2 losses in a row, so this one's kind of tricky. I had this loss this time when my threshold was set to 9. My window was 12. What's the rule say? Your new threshold is 1/2 of what your window size was. It's 12. Therefore, my new threshold is 6. And my window size, because it's a timeout, is 1. So I start over again. 1, 2, 4, 8. I can't do it again because I've crossed the threshold. Once I get to 8, that's my last. This jump was my last one. So I grow linearly now because I'm in congestion avoidance. So I grow to 9, and I have another loss. So I'm at 9. I have a loss. So my current window size was equal to 9, and my threshold was equal to 6. What's the new value of my threshold going to be? What's the rule? Correct. Where your window was, which is 4.5. So we're going to call it 4. What's the window size, the new window size that we're going to have? Well, it depends on the type of the loss. When I was at 9, I can see that it was a timeout because it went all the way down to 1. So this was case A. So I start over. I just set those 2 variables and I turn it loose again. Is my congestion window less than the threshold? Yes. My threshold is now set to 4, right? It'd be helpful if I drew this line. It'd still be how I drew it straight, too. All right, here's 4. So am I below the threshold? Yes, I am. Therefore, I can grow exponentially. 1, 2, 4. Now I've reached the threshold. I grow. This is a bug, so let's pretend it was a little higher than that. It looks like here they rounded up, and other times they round down. So Corot's has some light bugs in this thing, but let's ignore. He got to the threshold, and now he's going to grow linearly. So you're in congestion avoidance. Have a triple duplicate ACK, have a timeout. You always know a timeout because you go to 1. Every other loss is not. This is a timeout. Let's draw some more. There's another one. Timeout, 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 timeout. All the ones. This is triple duplicate ACK, triple duplicate ACK. Easy to spot. Timeouts go to 1. How many timeouts are in this diagram? Correct, 4. You see them? 1, 2, 3, 4. How many triple duplicate ACKs type of losses did I detect? How many times did I go downhill, but I didn't go all the way to 1? 0. In this case, it was 0 times. All right, let me ask you another question. For this snippet, what was my congestion window value when I experienced the loss? It's a little hard to tell without units. 5, 10, 15, 20. So what was my congestion window size? Am I going up one by one, or am I growing exponentially, guys? One by one. So you can see this one's on the line. So what's this one going to be? 17, right? It's got to be. You don't have to eyeball. Just count how many rounds you've gone past that. So my congestion window was 17. You already told me it was a timeout loss. So what was my threshold before? Doesn't really matter, because what you're going to do is set the new threshold to what? To half of 17. In this case, it's going to be 8. And what's my new congestion window size going to be? It's a timeout. Automatic answer, 1. So, all right, let's pick a different spot on here. And I'm going to ask you guys the same question again. It's weird. No triple duplicate X. Aha! Finally, we have one. Okay, how many timeout losses were detected by my transmitting TCP software according to this diagram? Right. Do I know there was a loss? How? So can you be more subtle in your definition? Do you know for sure what happened? Can you ever know what happened on the network? No. So the right way to say this might be it detected a loss, or it believes there's a loss, or it's decided that there's a loss. It helps to be careful, because you'll reinforce that oh yeah, because I can't really know. So you want to try to avoid saying, I lost a packet. Okay, now everyone's going to say I lost a packet. Okay, that's how everyone says it. But I want you guys to know you never know what happened. But even in the simulator that I showed you a minute ago, you can do fun things with this simulator, like pause it and kill off a packet and see what happens. So how can you say you don't know? You're playing God. You're the one that's doing this. And you can also kill off an acknowledgement and send it on. So it's kind of fun. And then what will eventually happen with the simulator, I can still send more packets, and I'll get acknowledgments, but there's a timer that's waiting for 2 and 3, and this thing is going to get impatient, and it's going to resend packets 2 and 3. And you'll see it happen. Now, it only really needs to resend 2, but it resent both. But the problems were different. With 2, the packet was lost. With 3, the acknowledgement was lost, right? You see down at the bottom, 2 and 3. 3 looks like the rest of them. It got packet 3. It didn't get packet 2. So it's going to receive 3 or receive 2 and throw out 3 because it's a duplicate. And it'll send back an acknowledgement letting them know, here's 2, and here, again, I reminded you, I already got 3, but the receiver never, or the sender never got 3. So he's going to be super happy when he gets these acknowledgments. He's going to slide his window all the way over, and I can send 5 more packets. All right, so how does that relate back to this diagram? I'm sending a windows full of packets every time, but my window's getting bigger and bigger and bigger and bigger until I burn my fingers, and then I back off. So if it was a timeout, I go all the way down to 1. If it's triple duplicate, which this doesn't show, then the idea behind triple duplicate ACK is I'll draw you a diagram to help you understand, because it's not hard to understand it at all. Here's my sender. He sends a bunch of packets. This one is lost. And these would all be sort of sent all at once, but I'm trying to make this where you can see a little bit of space between them, okay? So my window size is however big this is. So 1, 2, 3, 4, 5, 6, 7. So my window size is equal to 7 times MSS bytes. So we usually say a window size of 7. Just to make it easier, we say that. Packets 1 and 2 and 4 through 7 made it. Packet 3 was lost. What the receiver will do when this happens is he will receive packet 1, and he will send back an acknowledgement for it. And if I drew this the way it really is going to work, there would be a great deal more distance between here. There's a bunch of waiting time that I'm not showing. Because remember, there's transmission time is nothing. The propagation time eats it up. So I'm going to get an acknowledgement back for 1 and 2. And the acknowledgement for 1 is going to say, thank you very much, please send me 2. And the acknowledgement for packet 2 is going to say, thank you very much, please send me packet 3. Then the next packet is lost. So the receiver sends nothing back. But he keeps getting packets, right? He gets packet 4, packet 5, packet 6, and packet 7. So when these are arriving out of order, so what the receiver will do is store them for now and hopefully wait for this missing packet to show up. So he will send back the acknowledgement saying, thanks for the packet, but I will still like to see packet 3. I was waiting on that one. So this is a duplicate ACK. And then he gets another one, sends it back saying, I'm letting you know I got something by sending you an ACK, but the reason I'm giving you 3 in it again is to let you know I still haven't got packet 3. That's the next one in order that I was waiting on. Another duplicate ACK. He gets the third one, and here's the logic. My network is obviously not down. A lot of my packets are arriving because I continue to get acknowledgments back. If the network weren't working, how would I get acknowledgments back? I mean, there could be some crazy reason, but the most likely reason is because packet 3 got dropped, but the ones after it didn't. I can take a hint. Let's resend packet 3. When the triple duplicate ACK happens, which is the 4th ACK, you will resend the missing packet. And in the meantime, you get the acknowledgement back for 7, and again, it's still 3. But that's okay. You don't need any more hints. It's like, I got it, I know. Okay, you didn't get 3, thanks. And so you've resent it. You will wait, and what will end up happening when it receives 3 is interesting. All of these stored packets that the receiver was buffering, now that you've sent it the one that it was missing, it sends them all up to the application in order. Remember, TCP's job is to deal with all this garbage and to make the receiver believe that it's a perfect network. So mission accomplished. You've given them the packets in the same order that the application asked you to deliver them. You had to buffer them a little bit and do some stuff like that, but you pulled it off. So your window slides over. What happens back at the sender? The sender sent his entire window's worth. He had to resend one packet, but he's still waiting to get the acknowledgement back for this. When he finally gets the acknowledgement back, he can slide his window over and start worrying about the ones after 7. Okay. I'm concerned that you guys didn't get this. I wished I'd figured that out on day 1. We should have started with the semester with this. It's in the syllabus. It's supposed to be part of the class. But I guess I was the only one that was doing it. So I know there's a ton of stuff to cover, but I got to talk and figure out, like, why didn't this happen? Because I can teach it in here, but it has to be taught. It's fundamental to understanding networks. So you just got, like, the 30-minute summary review of what should be about 12 hours worth of instruction to understand this. And I'll show you some other examples to kind of figure out what's going on. But the best way to do it is just to kind of probe. So if I draw my window, this thing, where is it? It's way down here. This thing that I had before, where I was showing you how the windows get bigger and bigger and bigger with each round. I hit my, what did I just do? I hit my slow start threshold. So I was growing exponentially, 1, 2, 4, 8, 16. This is the size down here. I hit my threshold, and I started growing one by one. So round 6, 7, 8, I was only growing by one for each of these. I can draw that as that other diagram that I just showed you. So this is a window diagram. It's usually drawn horizontally like this. A timeline is not. A timeline is what I drew vertically a second ago. So we can draw a timeline here. And I got to think about how to do this without driving myself and you crazy. So round 1, I send a packet, and I get an acknowledgement back. I'm very happy. When I get the acknowledgement, because I am in slow start, for every acknowledgement I get back, I add 1 to my window size. So my window size was 1. I receive an acknowledgement back. Now my window size is 2. So I send 2 packets. The next round, I'm going to send 2 packets. And I'm going to get 2 acknowledgements back. When I get the first acknowledgement back, my window size is going to go to 3. And I get the next one back, and it's going to go to 4. That happens basically at exactly the same time. In fact, TCP is pretty smart about it. They may just send 4 and skip sending you 3, which is the same thing. So for each one of those I've added, now my window size is 4. So guess what I'm going to do? I'm going to send 4 packets. And they're parallel. And as I get the 4 back, my window size is going to grow from 4 to 8, 5, 6, 7, 8. And I have one more to do, but I'm not going to draw 16 lines. I hope you'll forgive me. So I'm going to draw, I'll try drawing like a thick line if I can do that. Maybe get away with it that way. And then I'm going to get 8 acknowledgements back. If you'll let me represent it this way, that would be awesome. So my window size is going to grow from 8 to 16. And now I've reached my threshold, my variable. The next window size I send is going to be what? 17. So I send 17 packets. I get 17 back. What's my window size going to be now? 18. How does that work? Because my window size was 17, and I'm going to get 17 acknowledgements back. For every one of them, I'm going to grow my window size by 1/17 of an MSS. So after I get 17 of them, I will have a whole MSS, and I will grow to 18. It's just as simple as that. You grow by byte numbers, and you end up with doubling it. So let's say while I'm sending 18, I have a problem. One of the packets is lost. Let's say it's packet number 12, and the rest of them are okay. So packet 12 is going to ask, or packet 11 asked for packet 12, and it never arrived. Packet 13, 14, and 15 showed up. They all said, thanks, but I was looking for 12. Triple duplicate ACK happens. Somewhere in the middle of this, and you're going to resend packet number 12 by itself. Window size is equal to 1. Just sending the 1 packet that's lost. Once that comes back, you're happy again. You got an acknowledgement for 12. You can go on and grow, but because there was a loss and you had a triple duplicate ACK, what's my next window size going to be? It was 17, and then it was 18 when I had the loss. So what's my new threshold? It's going to be 9, right, isn't it? Half of 18. And because this was a triple duplicate ACK, my new window size is going to be 9 as well, plus 3 with TCP Reno. It also always is going to add 3 to it. So my new window size is going to be 12. But I'm already in congestion avoidance. I'm going to go from 12 to 13. So these are tedious diagrams, guys, which is why it's normally something that takes a ton of time to kind of go over. I'm nervous. I'm just like totally losing you on it. But we don't have 12 hours to go over this. This would be the last thing we would do for the semester. And there's some other stuff that this class is responsible for teaching you in the syllabus. I mean, when I came to tech, I wonder if I can find this thing in here. Let's see if I can find it. Tech 28, here we go. Oh no, that's not quite it. I think it was a spreadsheet that I had. Yeah, here it is here. It is this one. I want to open this up and show you. Come on. Open it up. Very pretty pinwheel. We're very impressed. Here it is. My first semester. This is what they said it had to cover. So I went through a number of textbooks and marked down which sections each textbook covered. I ended up having to teach out of 3 because one of them taught all the basic stuff plus more, but had some gaps, and I used a different textbook to get some of the things in red, and then the third one to get the spectrum stuff. So it's in here. Flow control, sliding windows, go back in. That's exactly what we just looked at. Selective repeat, the thing before it, go back in. It's all right here. It's all part of that. So I don't get it. I don't know. Every instructor gets to teach the way they want, and I respect that. But I'm confused by that. Okay, so basically, as I look at the packets that are going by in Wireshark, I'm not going to exactly see this, but Wireshark will draw this graph for you. They will draw, and specifically the graph they will draw is this one. Wireshark will do it. If you tell it to watch a long transmission, they will draw this graph and they will show you at each point you can click on the graph and it will take you to that packet. It'll actually show you the packets that got sent. And the way that it knows what's going on is it looks at the time and it sees you send a burst of stuff and then you stop. That must have been a window's worth of data. And so it groups all those together as a dot on the graph. And then it sees some time go by that looks like the round trip time. And so it goes, aha, here's the acknowledgments coming back. They see it get acknowledged, and then they see you send more packets, one more than the time before, so they can draw another dot on the graph. It's a good tool for doing that. I can't ever remember how to get Wireshark to draw one of these graphs. Pablo is the world master of this, the other professor. If there's one thing that guy can whip everybody's butt on, it's getting Wireshark to sing. So he knows how to get it to do all kinds of graphs, and it's cool because I learned a lot of stuff that I hadn't seen people do except like in courses. So my guess is he's taught Wireshark before, but it will graph it for you. So you can collect tons of packets, like with Netflix, turn Wireshark on, watch a movie, and filter for a specific conversation. So it throws out all other packets except the ones between you and Netflix. And that's pretty easy to do. That I do know how to do. It's one click. And collect, I don't know, 100,000 of them. You know, wait an hour, 30 minutes. It might not take that long. And run that graphing tool. So I will try to build the graphing tool for you and give it to you guys as maybe as a homework. That's a fun homework. Turn Wireshark on. I'm going to assign you the task of watching a movie on Netflix for networking class. How cool would that be? And I don't even care what the movie is, but it needs to be from a site that's got capacity, and I would like for you to do it from the most congested place you can think of. Maybe it's on campus, maybe it's at your house, but find some place congested and collect, packets for 20 minutes, let's say. Filter all of them out except the ones that you want, and then look at how to graph it. So I'm going to start grabbing packets. These are going to go between here and WebEx. I don't see lots of retransmissions happening, but maybe every once in a while there will be one. It's only for TCP. So I'll let this run for a few seconds. I've got 2,500 packets, 3,000 down at the bottom. I can see them as well. And the way you do a conversation filter is you control-click or right-click on any row. I happen to know that 66 is WebEx, one of the Cisco addresses, and I say make a conversation filter at the, whatever level you're at. Now, in this case, WebEx is going to mess with me because they're not using TCP at all, and so there's no windows. They're sending just UDP packets. So you have to find like a movie site or somebody that's sending TCP. So let me see who this is. Who is this? IP, do I know who this is? Who owns, let me see who this is. And if not, we're going to try going to a completely different site here. Who owns 209.197.201.7? I bet it's Dropbox. How much you want to bet? Oh, it's WebEx as well. Okay, that's kind of surprising. So let's set our conversation filter at the TCP level between these two hosts. So it'll give you all the ones, sent, receive, sent, receive. There they are. And what I want to do now is, let's see if I can figure out, I don't know what this will do. This is not exactly, it's going through the entire thing. So I need to do my homework a little bit to give you guys something that's doable. But what it's showing you is that transmission table with the two sides. It's making all the lines horizontal. It's showing you the sequence numbers. It's telling you the length. And then it's showing you acknowledgments that periodically come back. Here's a couple of acknowledgments that came back. Here's 3 more packets that got sent, 2 acknowledgments, 3 more, on and on and on. And the problem is, it's not just showing me TCP, it's showing me all the packets. UDP, TLS, all this other garbage. So I got to figure out, oh, let's try this. Let's see what this does. Did it change it? Yes, it's all now TCP. And let's just look at TCP flows. All right. All of these have push flags set, which means send it immediately. Don't accumulate a bunch of stuff. Don't wait for the window to get full. That's what you'll see with video and audio. They're impatient. They want it to get sent quickly. But there's a whole bunch more TCPX. And I don't know how to draw the graph. I'm not that good at doing it. But I'm sort of in the neighborhood. Okay, it's past time to take a break. You guys want to take a break? And then we'll come back and sort of regroup, figure out where we are. I'm going to ask you guys, like on a scale of 1 to 10, how much of this do you grasp? I could just give you some homework problems to kind of go through and label stuff, but I want to go through a couple of more examples so you don't feel totally lost. Because what I'm going to have you do is go to that simulator, pick out a graph for yourself, and I'll tell you what to label. I want you to label congestion avoidance. I may give you everybody the same graph and build it myself. That's often what I do. And then have you go do the other one. I'll just have you label, like, what was the window size here? Remember, here's the rule. What type of loss was this? You can tell by looking at the graph. If I had another loss here, what would you set the window size to if it was a timeout? And can you extend the graph by 1 more dot? Something like that, so you can get at least the fundamentals and get your arms around it, because you need to. If you guys ever took another lesson in this stuff, you'll get lost. God help if you ever get asked in a job interview. You tell them you take networking from a guy that worked at AT&T for 30 years and then retired from Cisco, and you can't even tell him how TCP works. I'll stab myself in my leg. Right? That just cannot happen. I've had lots of students come and tell me over the years, that interviewers told them, you're the first person that knew the answer to that. So that's why you got the job. And, you know, I mean, thousands of students and like 6 come and tell me, but that's still something, right? So I just don't want you to go and say that you learn networking and then have somebody ask you a really fundamental, important question and you not know how to answer it. So I'm delighted that we figured this out. But I'm not quite sure how much I need to peel the onion back for you guys to at least get enough rudimentary to survival mode. So maybe this is enough, right? All right, let's take a break. And it's 7:40. Let's come back at 7:55. We'll spend 30 minutes when we get back. Does that sound all right? Okay, does anybody think it'll still be light, or is it going to be dark? Think so? Do we have a light? Anybody else? You all think it's going to be light? This is how it works. One person says it, and everybody backs them up. That's cool. You know what? You guys are more like that than the students in the U.S. are. That's a cultural difference. It's one of the things I love the most about students here. So this I/O graph, which is what it's called in Wireshark, it isn't quite the same thing as rounds and window sizes, but it does at least show me the number of bytes I'm sending in a second. And you can click on, there's a way to get it to spill the beans and go to those packets. Go to packet under cursor. And so there it is right there. And if I move this over and go to another one, it's supposed to switch it. It's not. And I remember having this problem before. So it's all coming back to me now, but I still want to find one that shows that traditional scale. So if I can pull it off, I'll give it to you as a problem. Okay, so if I gave you a graph and I asked you to tell me some of the variables you think you could pull it off. Like if I asked you to draw something like this, or this, or this, do you have any confidence that you could do it?
No.
I would be more worried about that.
This one? Okay. What about this one? A little better?
I don't see that.
You are not like
Yes, that's better.
Okay. Yeah, you can't see the. Can you see my cursor when it moves around on the screen?
No, yes.
Okay. Gosh, you made me nervous there. I was wondering, like, could you ever see my cursor? Because I do that all the time. I'm like, have people never been able to see what I'm pointing at?
It's because it's like very small.
It's like sometimes I'll point at the screen with my finger, like somehow WebEx is going to capture that. Like the camera's going to come out and point down in my hand or something.
Why not?
It's like crazy. All right, so let me go over a couple of the fundamentals again with you guys to arm you for battle. We can build a table that kind of lists this stuff out. And that's not tall enough. Maybe this is too big. I don't know how many variables I'm going to need, so I'm going to just draw out a few of these things. So we're going to have round, transmission round. Do you know what that means, round? Just like, which iteration are we? All right. So maybe I can draw, maybe it would be nice to draw some vertical horizontal lines in here so we can kind of keep stuff straight. There's probably an automated way to do this. But we'll need a bunch of lines.
You only have computer to do that?
What do you mean? That's the only thing I use it for? Is that what you're asking? I have Excel sheets that'll crank the stuff out, that'll draw it, but I don't want to have to go find them and open them up right now in the middle of all this. All right, so So start off with our congestion window size, and we'll ask at any given point, are we in congestion avoidance or are we in slow start? And we start off with slow start. We need to know the value of our threshold to answer that question, and we need to know, I'm going to leave some stuff for now. So let's say our threshold is 8, okay, when we start off. So in round 1, how many packets are we going to send? You always start with 1. Why not? Might as well start at the beginning. And is that slow start mode or congestion avoidance? We're starting. Which one has the word start in it? All right, so this is slow start mode. So I get an ACK and get it back. What's the rule for how we grow when we are in slow start? Do we grow exponentially or do we grow linearly? Yeah, see, we grow at the beginning, the very beginning, we grow exponentially. So I'm going to go from 1 to 2 to 4 to 8, correct? And I'm going to stay in slow start mode this whole time. My threshold is not going to change because I haven't had a loss. In fact, it'll never change until I have a loss. That's the only reason that the threshold will change. So the next round is round number 5. I'm now in congestion avoidance mode because I passed the threshold, but it's still got the same value. It doesn't make the number change. So what is my window size now? I was at 1, 2, 4, 8. I was growing exponentially. Now I'm in congestion avoidance mode. So what's my window size going to be now? Linear. So I send 8 packets. I get 8 acknowledgments. Each one of them causes me to grow by 1/8 of an MSS. So if my MSS was 100 bytes, for example, the first packet's going to acknowledge 12.5. It's going to cause it to grow 12.5, then 25, then 3750, then 50, etc. I get through 8 of those. I've grown another 100 bytes. Right? So it does it in pieces. But I don't know what the MSS is right now because I'm not asking you what that is. We'll do that in a second. But what I do know right now is I'm going to grow linearly. So until I have a loss, I'm just going to grow my window 1 by 1 by 1. I'm going to stay in congestion avoidance forever and ever and ever until I have a loss. So let's say total packets sent, because your file that you're trying to send, I mean, the application doesn't know any of this stuff is going on. The application gave you a 5 megabyte file and your MSS is 1,000 bytes apiece. You can determine how many packets it's going to take to get your file across to the other side. And what you want TCP to do is hurry up. Get them there as quickly as you can. So let's say we needed to send 60 packets. Okay? How many have we sent at each round? 1, 3, 7. I said 7, but I wrote 4. 15, 24, 34. Do you see I'm getting these numbers? So not quite 60, but I'm really close. It's the cumulative size of my congestion windows as I've gone along. I just keep adding this number here to the total. So if you told me your file size and I told you the MSS, we could calculate how many packets it would take to send. Right? And that's basically what you're trying to hurry up and figure out and do. So let's say at this point there is a packet loss, and the type of loss is a triple duplicate ACK. And actually, it's going to happen during this round. So it's going to change some things. Triple duplicate ACK. And the rule for triple duplicate ACK is to take the new threshold plus 3. If it's a timeout, and you saw that in the simulator that we used, the timer went off, then it's going to basically be 1. This is your new congestion window size. The threshold, the new threshold, is always going to be the same. The threshold is equal to the window size divided by 2. So let's apply those rules. We need to calculate this and this. So what's my new threshold now? It was 8. What is it now? I heard it. Somebody said it? I think somebody said it. What's the rule for my new threshold? SS threshold? The size of the congestion window in the round where the loss occurred divided by 2. So the loss occurred in this round. What was my window size? So divided by 2 is 6. So my new SS threshold is 6. And I'll make it another color so it sticks out more. Okay? To figure out whether I go back into slow start or congestion avoidance mode, it's going to depend on whether my new window size is above or below the threshold. Below the threshold, your slow start. Above the threshold, your congestion avoidance. So what is my new window size? It was a triple duplicate ACK. I know that because it says that right here. So what's the rule for triple duplicate ACK? Your new window size is equal to your SS threshold plus 3. Well, 6 is the new threshold. So it's going to be 9, isn't it? Is that right? 6 plus 3 is 9. Am I above or below my threshold? So I stay in congestion avoidance mode, which means the next round is going to have how many packets? I'm above the threshold, so am I growing exponentially or linearly? Linearly. Remember, the top of them always look like that. The mountain tops are all linear. So to go linearly from 9 takes me to 10, doesn't it? And my total number of packets gets off track at this point because I don't really know when the missing packet was sent, but I just assume that it was. They figured it out and they resent it, so I'm going to stick with 57. The next one's going to be 66, and then 76, and so forth. So if I gave you some rules and said, fill this table out, here's your initial threshold value, you're going to have a loss with packet number 55 or 52, something like that. I'll tell you the packet number. The 52nd one you send, you're going to come down this list. You'll have to fill this thing out. You'll come down the list and you'll see the 52nd packet loss happens during this round. So we're talking about round number 8. Okay? We pull that off. I'll leave all the sequence number garbage out. We should do that as well, but we're not going to. We don't have time to do it. I will, however, teach it to you for a minute, okay, so you kind of get an idea. Because I've always told you that TCP counts bytes. It doesn't count packets. All this is packets. This whole table is packets because that's how we teach it. But what we really need to know is bytes. So here's the way it works. We have a starting sequence number. It's a randomly selected number between 0 and 2 to the 32 minus 1. So it's big, between 0 and 4 billion. It's random, so nobody can guess what it's going to be. So let's say my starting sequence number is 10,000. Nice round number. And let's say the size of a given packet is 1,000 bytes. Okay? So when I build a packet and I send one of these things, I have to put a sequence number on each packet. And it's going to grow by 1,000 at a time. But I'm showing lots of packets at once. So what I'm going to show you is what is the first sequence number for this window for the first packet. The first window packet sequence number. Well, the first one's going to start obviously with the beginning, 10,000. I send 100 bytes from number 10,000 to 10,999. That's the 1000th byte. So the acknowledgement I'm going to get back for that first packet is basically going to be 10,999. And that turns out to be the last byte, the last packet ACK. And the way acknowledgements work in TCP, when they thank you for sending them bytes, they ask for the next one. So for this first round, I started with my first packet with byte number 10,000. That first packet ended with byte number 10,999. That was the one and only packet in my window. Therefore, the acknowledgement is going to ask for the next byte, which is going to be 11,000. Agreed? Now, starting at 11,000, I'm going to send two packets with 1,000 bytes each. The first one's going to go from 11,000 to 11,999. The second one's going to go from 12,000 to 12,999. So the acknowledgement is going to be, I'm ready now for 13,000. I'll get two acknowledgements back, but the last packet, the second one in this case, has that ACK. I start at 13,000. I send 4 packets. I'm going to be ready for 17,000. So after the 4th packet is acknowledged, I get a request to send starting with 17,000, and so forth. You see the pattern? Could you fill this out? I won't make you. This won't be part of our problem. But all I did was I took the number of bytes that could fit in a packet times the number of packets in this round and added that to my starting sequence number. I added 1 to the end because that's what Reno does, and I got the next sequence number that I want. The acknowledgement is the next sequence number. So down here in this one, if I broke this out, we'd have to go packet by packet by packet to see what happened. But what you would see is you would start getting duplicate ACKs in here. This table's not good at showing it to you. It would be enormous. It would have, at this point, 76 rows in it. I'm not drawing 76 rows. I love you guys, but I'm not that much. I'm not going to draw 76. Okay. So I'm going to teach the other sections how to do this much. We'll cover this material. I have to give you some of the stuff. So that's one thing I'm going to give you, okay? Another thing I'm going to give you is something to do with this. So I will probably draw one of these things out and ask you some questions. You know, circle and label the points where there's a timeout. Circle and label the points where there's a triple duplicate ACK. Like that. Tell me where you're in congestion avoidance between here and here. Tell me where you're in slow start between here and here. Something like that, okay? And I may ask you to draw a little bit more. Okay. I'm not positive we have a bunch of time to start something else new. Let me see if I can show you a couple of helpful tools that might help you figure this out, and then I'm going to try playing with this a little bit more. Packets per tick. That's probably what I want. Okay, so we looked at the selective repeat protocol. That's a decent one to help you see what's going on. You can try sending packets and getting them back, but I'll have to drop the URL out for you guys. So what I'm going to do right now is to do that. All right, there it is. It's in your class folder. All right, let me go back to Wireshark. And what I'm going to try to do is close this and go to the site that my son sent me. Ugh. Fine. All right. Where's the Yankees? There we go. All right. When I click on this, I want to be grabbing packets. I don't know if this will work. And if it does, I don't know if it'll be TCP. Okay. This is the baseball game in Houston. What I'm hoping is that we're grabbing, well, the packet count's really going up fast. And it looks like it's all TCP. Liking the score. That's good. My son told me that the Yankees hit a home run, and that was the last thing I heard. So we've gotten back on top.
Hewlett tries one to left field. Back goes Frazier on the track, and he makes the play in front of the wall. That'll do it for the Astros. But Jose.
Okay, done. Enough of that. So we'll stop and see if we can finish on a high note today with the IO graph. I think that's what I want. Oh, not yet. I want to get rid of this filter. Oh, here's all the missing packets. 209, I think, was WebEx, wasn't it? Didn't we decide that was WebEx? Reset root 66 is definitely WebEx. 104.27, maybe that's it. $144.59. All right. Yeah, bad web host, anti-hacker alliance, Cloudflare, gotta be it. Conversation filter for TCP, I hope there's a bunch. 50,000 packets that time. So now I'm going to do an IO graph. With just is this all of them? Packets per second. Yeah, so this went everywhere from basically 1. The highest it looks like it ever got was about 2,450 packets in a window. That's a lot of packets in a window. Don't want to draw that. Don't worry, I will not give you that. And it's just the ones that are shown. There is supposed to be a way to set some of these intervals differently, though. Bar line, y-axis is packets, that's fine. Can I pick something different here? I can if I double click on it. Let's see what I can get. Window size? Come on, guys, you're killing me. Count frames, fields, y-axis. No. This would be good enough. So you can kind of get an idea. They're going all over the place. They have losses, and they have sustained losses that go on for a long, long time in here where nothing's happening. When you go back to your original graph, you can see it in the bars on the right once it shows them again by colorizations. They look like black and red, typically. Duplicate X. So what does duplicate X tell us? Here's some duplicate X. What's going to happen when you get duplicate X? Uh-oh, we're in trouble already. you're getting acknowledgments for packets after a missing one, and they're telling you, thank you for sending me the packet, but what I was really looking for was 241. So here they're counting them even for you. 241 number 1, number 2, number 3, number 4. Wireshark is adding all that stuff in there. It's telling you, you sent it this packet, and you got a bunch of duplicates back. So what I would expect to have happen is that you're going to resend it again. You'll start over down here. You'll see TCP go, okay, I get it. So triple duplicate ACK. When you see duplicate ACKs, TCP, if it gets enough of them, and it did here, it'll resend the packet long before the timer goes off. The timer's set to be really, really long. So if you still haven't gotten acknowledgments by the time you set the timer goes off, it's bad. So drop back down to 1. The network is probably congested. So to climb all the way back up to where we started this an hour ago, this behavior of reacting to losses and being very careful about growing linearly when you believe you're close to the capacity of the network and resetting your threshold and window size so that you stay within that zone is how TCP keeps from overwhelming the network. As for whatever reason, if the network starts to get full and a packet gets dropped anywhere along the way, you will detect that when the timer goes off or you get triple duplicate ACKs, and you will slow down. And therefore, wherever the problem is, maybe it was router number 17, you'll give it a breather. You'll give it a chance to catch up. Because if it's dropping your packet, it's dropping lots of other packets from lots of other TCP streams that are arriving from lots of other different ways. And they will all detect that their packets are being dropped, and they will all back off as well. So the community will kind of, whose packets get dropped is random. It won't be all packets. It'll be some here and there. The more congested it remains, the more people's packets getting dropped, and they will just keep shrinking and shrinking and shrinking the amount they send. And where you will end up is exactly where you should be. You will have 1/n of the bandwidth across n users. Magic. That's how it works. If you try to use more than your share, so will of someone else, you'll get backed off. So you spend your day oscillating back and forth between 1/2 of the bandwidth and all of the bandwidth. So if I draw, you'll hear this called this, if you talk to anybody with TCP, they'll say TCP has a sawtooth behavior. So this is half of your fair share of bandwidth. This is all the share of bandwidth, and what you're going to do, ideally, is go up like this all day long and back off down to half. All right, so what's the average of that? You can see it with the naked eye. Exactly right, 3/4. So your TCP stream will get 3/4 of what you deserve. And that helps create a little bit of buffer for the routers to catch up. Everyone's doing this. Everyone's getting it set. If you look across a bunch, you'll see the same thing. It's hard to do without a good simulator package because we can't run a bunch of Wiresharks on different connections at the same time. But that's, man, that's like speed TCP windowing 101 or something. I don't know what to call it. I hope I never have to do that again. However, I'm going to have to do it 2 more times this week, right? Because I've got to duplicate what we did here with the other 2 sections. So my poor slides, my poor plan. We got up to we got to slide 22 at least out of 69, and the rest of this may be helpful to you if you want to poke around a little bit. It kind of goes through and tries to talk about some of this stuff, but it's not really the right way to get started on it. It's not the slides I would have wanted to go through with you guys. Okay, that's it. We're adjourned. So have a great Semana Santa, and I'll make the homework due the day you get back. No, I'm kidding. I'll make it due the day before you go. No, I'm kidding. I won't do that either. I'll be, you know me, I'm teasing. I'll be nice. The grades are good on the exams. I didn't have 100. I had 99s. I haven't quite finished. There's a few I still got to do. I'm still expect I'll find a 100. The low grade so far was a 75, and the average is 93 or 4. So there's a couple of glitches, and those students will have a chance to kind of do some extra credit to pull it up. Because you remember my commitment on day 1, right? Stick with me, go to the labs, do the homeworks, do the tests. You will not fail the class. You'll get a grade where tech will not ask you to take it again. It will count towards your degree. You know, you don't want to see me twice, and that's probably true in the reverse. Because it would remind me of my failure. So, all right, guys, thank you very much. See you out there in WebEx land.